talk about the math behind machine learning. Now, before you get scared, notice the little cartoon there. It's really not as scary as it sounds. We could talk about artificial intelligence, and that sounds really cool, but actually artificial intelligence is pretty much machine learning, which is what the term we're using. That's what we're talking about here. But reality, machine learning is just a way of doing statistics. So that means if you can understand the basic concepts of statistics, you can understand the math behind machine learning and artificial intelligence. Before we look at some of the details, we need to get a big picture view of what we're talking about. So what is a mathematical model, or what is a predictive model? If you watch the video on what is the difference between supervised and unsupervised machine learning, you'll remember that supervised learning spits out a predictive model. So we need to talk about what is the predictive model. And you're working with computers and machine learning statistics, that means by extension a mathematical model. Well, first of all, what's this? Hopefully you can recognize this as a map, right? Now, that may seem kind of dumb, and the question I'm going to ask may seem kind of dumb, but think about it. Is the thing pictured on there, is the thing on that map an island? Is it a treasure island? No, it's not. It's a representation of an island, right? An island is a thing that is a 3D thing, it's physical, it sits in the middle of water, and you can go and you can sail to it. This is a map which represents an island, but you can't sail on that map and go to the island and walk on it. Why is that important? Because we're going to be talking about, and to understand mathematical models of language or AI in general, you have to understand this idea of representing other things in the shape or form of something else. And particularly in this idea that you can take something that is 3D and represent it on something that is 2D. And then if you notice on the map there going down and across, you have letters and numbers. And of course you probably know that's to help locate something on the map. So we can use a graph to represent something that is 3D as something 2D by using this graph. And we can keep the proportions the same, and it can be very useful then for finding. You can actually measure the distance, right, on the paper, and then do some calculations and get the actual distance that in the real life what it is in the 3D. This is a model. And in some sense it's a mathematical model. We can do this for language as well, but kind of the opposite direction. Language is not something that is 2D or 3D. It's some sort of dimension, I guess. It's not a location on the globe, but we can take it, we can take the words and the information, and we can think of it in the opposite way. So here's a 3D thing, a thing on a 2D representation. We can take something that is not 3D and represent it in a 2D or even a 3D space. We can think of data, any data for that matter, as dots on a multidimensional space. So two-dimensional space on a plane, or three-dimensional space like in a sphere. So that is a concept that actually took me a long time to grasp when learning computational linguistics, because I just didn't understand this idea of taking language and representing it in a three-dimensional space, for example. And then of course once you do that, you can use numbers to map where things are, just like you can on a map, right? So you can have numbers one way and numbers the other way. And that's nice because once you put in numbers, you can do math, and it turns out that you can take things that are not numbers and do useful things with them. So here's another example of a model. You may not be able to read that, but what we have here is up and down the y-axis, a percentage of nutritionists that say that a certain food is healthy, from 0 to 100% at the top. And on the x-axis going across, we have the percent of all Americans who say that a food is healthy, that same food is healthy. Now, one thing to note real quickly here, of course, is that they did not go out and talk to every single nutritionist in the world, and they did not go out and talk to every single American about what food they thought was healthy. They took a reasonable sample of the population and did a survey of them. And this may be a little bit hard to see, but some things here that might be interesting is that you can see this linear diagonal line showing the correspondence. So the rough pattern here is that generally, if Americans think it's healthy, nutritionists agree, and generally if Americans think it's not healthy, nutritionists would agree. But you can see some other information here too, like those outliers there down kind of in the bottom corner, like frozen yogurt. Turns out that's further down the x-axis, right? So more Americans, general Americans would say that frozen yogurt and granola bars and coconut oil and granola are healthy, and nutritionists actually wouldn't agree, which is very sad when I found that out, that granola bars are not as healthy as I'd like to think they are. This is a model. This is a model of this information. You have 2 dimensions. You actually have 3 dimensions because the images themselves is another dimension, right? If it was purely 2-dimensional, we wouldn't distinguish between the types of food. We would just show the dots like a food represented on there, and we'd be like, yeah, see the general correspondence between Americans and nutritionists and what they think about whether food is healthy or not. So there's actually a 3rd dimension here. They chose to not use numbers, not use a numeric scale, because it's harder to do that on a flat screen and use images instead. But it's a model. So it's a multidimensional model of information. And we use some numbers there, partly because the numbers are part of the data, but also because the numbers allow us to plot this in a 2-dimensional space. So this is a model of the information. Now, where does the predictive come in? Well, it's just like we learned the basics of predictions, or basics of probability, right? You count what happened in the past, you divide by total occurrences to get some sort of proportion, and then you make this assumption that what was true in the past for a certain sample of the data will be true for all data in that same context, and you make a prediction. So if we took this, right now it's just a count or a description of what is true for a sample of Americans and nutritionists, and we turned it around and went on the street and said, this is true, let's assume this is true, and we went to nutritionists and general American population and we said, you think, you're an American who's not a traditionist, you think that frozen yogurt, what's the number there, like 60, right, 65. So we say, we choose 65% of the Americans we talk to and say 65% of you think that frozen yogurt is healthy, but only 30% of our nutritionists think it's healthy. And we're saying that as a fact, we're making that prediction. And then if we went and counted and found indeed that of our sample, or if we could get all the nutritionists and Americans to talk to, indeed 20% of the nutritionists do think that frozen yogurt is healthy. Only 20% think it's healthy, whereas 65% of Americans think it's healthy. Our prediction max reality, and we have not just a predictive model, but we happen to have a good, useful predictive model. So when we talk about machine learning and supervised learning providing a predictive model, that's what we're talking about.